Hello, I'm Hongrui. Today I'm going to introduce the work MPC-in-Multi-Heads, a multi-prover zero-knowledge proof system, or how to jointly prove any NP statement in ZK. This is a joint work with Kaiyi Zhang, Chen, Zhen Liu, and Yu. This is the outline of today's talk. Let us begin with the motivation of this work. Consider the following practical application scenario where we have a corporation with a Z-value contract and he seeks financial assistance from three banks. Suppose by separate negotiation, the banks agreed to lend the corporation X1, X2, and X3 amount of money. Note that in this situation, the exact amount that each bank agreed upon is considered sensitive information by the respective banks. In particular, they do not want the other banks to learn such value. However, a malicious corporation might exploit this information opacity and demand to borrow from those banks such that the individual values from each bank does not exceed the contract value Z, but they sum to an amount much greater than Z. In practice, this problem is called double financing, and to prevent this attack, the banks need to prove to a regulatory authority that the sum of their respective lending values does not exceed a threshold of the contract value, say 90%. Here we can see a dilemma between utility and privacy. By sending those values directly to the regulatory authority, the banks can easily show that the relation holds, but this puts additional trust on the authority. On the other hand, the authority is actually not interested in the exact amount the banks agreed upon. It only needs to be convinced that the relation holds. Notice that if there is only one bank, a classical range proof offers a perfect solution, but the existence of multiple banks complicates this matter. In conclusion, this kind of application scenario requires an efficient multi-prover zero-knowledge protocol. Moreover, it would be even more convenient if the banks can jointly generate a non-interactive proof. The authority or verifier is not required to be online during proof generation. Once generated, the proof can be posted on a public website or blockchain from where the authority can retrieve and examine at any time. In summary, the required functionality can be shown as a n+1 input function, fmpck. This function returns the relationship on the verifier's public input and the concatenation of m-provers inputs. As a sanity check, if we set the number of provers to be 1, then this functionality describes exactly the traditional single prover, single verifier zero-knowledge proof. What's more, if the verifier's messages are only public random coins, then the role of the verifier can be emulated by the provers using the Fiat-Shamir heuristic. Next, we investigate related works in the MPC and ZK literature. Since we described the functionality we need by a multi-input function, we can use existing secure function evaluation protocols in the MPC literature. Indeed, the GCZK construction follows this idea. Nevertheless, we find this approach has a drawback that the messages in most secure function evaluation protocols are not public coins. This property prevents us from applying the Fiat-Shamir heuristic and thus achieving a non-interactive proof. The next idea is to evaluate the zk-SNARK proof generation circuit directly using MPC. This allows us to bypass the above inconvenience. Nevertheless, the downside of this approach is the prover's computational complexity in zk-SNARK would correspond to the prover-wise communication complexity. We anticipate the concrete efficiency would render this approach impractical. Next, we investigate the verifiable MPC or PV-MPC. This primitive is actually very close to our goal. A PV-MPC protocol allows any external party to verify the correctness of a multi-party computation process. If we let the provers to compute the verification circuit and manage to make this process publicly verifiable, then our goal is achieved. After researching the PV-MPC literature, we find existing works have some significant drawbacks. Specifically, some works rely on a construction called bulletin board to facilitate a reliable broadcast, but in the ZK literature, we normally do not introduce this construction. Some other works rely on specific MPC protocols, but we want to get a general result. Finally, we investigate a work called ZKP on circuit shared data, which is proposed by Bonnet et al. In this model, the proof instance is shared among multiple verifiers, while the prover holds the entire input statement. We consider this work to be orthogonal to ours. Next, we introduce our construction, which we call MPC-in-Multi-Heads. We begin by revealing the original MPC-in-the-head construction of Isha et al. The overall idea is to construct a zero-knowledge protocol using a larger-scale MPC protocol. The prover holds all information required to verify the validity of the input statement. The idea is to let the prover locally generate and commit to a multi-party verification process, and let the verifier checks the validity of this process by opening some of the virtual party's views. In more detail, the prover secret share its witness W into multiple shares. Then the prover can locally compute the multi-party evaluation of the circuit, defined by running the original verification circuit on the summation of virtual inputs. After generating the views, the prover commits to those views using a commitment scheme and sends the commitment to the verifier. Then the verifier randomly samples a subset of the virtual parties and sends the index to the prover. The prover then opens the selected indices using the commitment scheme. Finally, the verifier checks the consistency of the open wheels. In more detail, a virtual wheel consists of the input, random coins, and all incoming messages during virtual execution, and thus the verifier can locally run the code of the virtual party again to generate all outgoing messages, which can be checked against the reported messages in other open wheels. If the views are consistent, the generated messages and reported ones should be identical. The verifier rejects if any inconsistency is found. Now we extend the above protocol to a multi-prover case. Notice that in the original protocol, the main job of the prover is to simulate a multi-party computation process. If the multiple provers manage to acquire the virtual wheels, then the rest of the protocol can follow exactly as the original case. So we should focus on how to acquire those wheels. We extend the original protocol as follows. We let the prover split their inputs into multiple shares and emulate a subset of the virtual parties. During the simulation, messages inside a subset can be simulated locally, while messages across different subsets must be actually transmitted by real provers. In this way, all virtual wheels can be simulated. Let us take a concrete example. Suppose there are three provers, Alice, Bob, Charlie, with inputs A, B, and C respectively. According to our construction, each party splits their inputs into three shares, and they would jointly emulate the nine-party computation process. We should note that during the above proving process, we need to prover's input privacy during the interaction process, which doesn't need to be considered in the original case. Next, we introduced the experiments we performed. We tested 3 relations. The first one checks the exclusive OR of 2 witnesses is the hash pre-image of the public information Y. The second relation corresponds to the double financing problem. In particular, it checks the sum of the pre-images of hash commitments is larger than a public threshold. The final relation is a simple summation. We instantiate the virtual MPC protocol using semi-honest GMW. The verifier checks two virtual wheels in each round, and the process is repeated multiple times to achieve a small enough soundness error. The experimental result is summarized in this table. The 2 numbers in the circuit size row denotes the total gate counts and the multiplication gate counts. The 2 numbers in the simulated party row denotes the number of provers and the simulated parties per prover. We conclude this talk by listing the contributions of this work. In this work, we proposed a new primitive called multi-prover zero-knowledge that arises from practical application scenario. What's more, we find the classical construction of MPC in the head can be easily extended to the multi-prover case, resulting in the first efficient construction of MPZK. Finally, we implement the protocol and performed experiments on it. Since we only utilize the most fundamental constructions, the performance of this protocol is inferior to the state-of-the-art in the zero-knowledge literature. Nevertheless, considering the active research in the MPC in the head paradigm, we expect further improvements by adopting those optimizations. This is left as a future work.